All right, guys, good morning. Happy Monday. Hopefully you enjoyed some of this sunshine this weekend. Kind of looking at what's coming up. So we are starting our last unit of chemistry that we're going to get to this semester. We skipped Unit 9 and went to Unit 10, simply because this you would be able to use with more upper level science classes, whereas Unit 9 was a little bit more chemistry specific. So I do have the full calendar up to date. Miss Kincaid's guys, you guys have the lesson plan, but it's laid out the exact same. So this unit is dealing with solutions, acids, bases. So acids and bases are types of solutions, but we're going to look at some properties of solutions first before we get into the acids and bases. So you can see this is a 2-week unit. So today we're going to start out talking more about water and solutions themselves. And then based off of what we do today, you'll be able to start that Unit 10 Part 1 homework. Looking at the due date, so the Part 1 homework is going to be due on Wednesday. And we're doing a lab Wednesday that will be due on Thursday. And you guys will have a quiz on this Part 1 stuff this coming Friday. We'll start on the acid-base stuff Thursday and into next week. And your test on this last unit will be next Friday. That will give us a couple of days to review for exams. And one thing that we learned Friday, so I know originally I told you guys your exam was going to be on Friday the 21st. The county does not want us giving an exam on a completely asynchronous day. So that first period exam will be on the 20th. So it will be on that Thursday instead of that Friday. So we will actually have class that day so we can review a little bit. And then whenever you get a chance after you get home, you can take your exam. So just kind of letting you know how everything plays out. And review, we'll do a little bit of reviewing class, but a lot of it will be kind of time. If you owe me makeup work, you can get that taken care of. There will be stuff that you can kind of practice on your own, have time to ask me questions, things like that. All right, so let's go ahead and get started. So today we're going to be focusing on the in general, like water and solutions, looking at some of their properties, knowing how to make solutions, how we dissolve substances in one another. So we're going to start off talking about water. Water we've actually dealt with pretty much all semester long. Water is what we make most of our lab solutions with. Most reactions do occur in aqueous solution or in water. And some things that we've talked about dealing with water throughout the semester. So whenever we have water as a liquid, we did talk about water whenever we did bonding. So remember, water has that bent shape. So it has the 2 hydrogens and then 2 electron pairs on the oxygen. That was one of those structures that we drew multiple times. That shape is going to be important for some of the properties of water. We also talked about water being polar. So remember, polar substances have that difference in electronegativity. So it has a slightly positive end and a slightly negative end. So water, since it's polar, is going to be attracted to other water molecules by those strong dipole interactions, which in water were the hydrogen bonding. That hydrogen bonding in water pretty much controls all of the special characteristics of water. So we're going to look at a couple special characteristics, and we're going to talk about how they kind of work. But we're going to look at water has a high surface tension, so we're going to look at kind of why that occurs. and water has a low vapor pressure. So we're going to look at what that is and how that occurs as well. But both of those are going to be related to those hydrogen bonding. So looking at water's higher surface tension. So surface tension is the inward force or pull that tends to minimize the surface area of a liquid. So what happens is whenever you have a drop of water on a surface, there's an inward force trying to keep all of that kind of beaded up and held together versus spreading out into a large puddle. So that inward force is that surface tension to hold it together. This is where liquids will bead up. So everyone's done kind of the lab where they do drops of water on a penny and it kind of bubbles up versus spreading out and everything. In water, the high surface tension is caused by those hydrogen bonds. So remember, the hydrogen bonds are trying to hold one water molecule together, or to another, excuse me. So they're being held together, which means they're not willing to spread out. So it has an unusually high surface tension when compared to other substances, because it not only has the normal surface tension pulling inward, it has that hydrogen bonding, which is pulling those water molecules towards each other even more. All liquids have surface tension, but water's unusually high because it has those additional hydrogen bonds. And it will hold a drop of liquid as a flattened sphere. So kind of like what we drew here, where remember a sphere is a 3D circle going around. So it's like you cut that in half and it will try to keep all of that water in that three-dimensional half sphere. All right, I think everybody's with me. All right, so whenever we're dealing with surface tension, it is possible to kind of break apart those forces to where a liquid will not stay beaded up anymore. So you can decrease the surface tension of water by adding a surfactant to it. A surfactant is going to be any substance that can interfere with those hydrogen bonds between the water molecules. So once those hydrogen bonds are kind of broken and you only have the normal surface tension pulling in towards the center, you're not going to be able to hold as many water molecules in that bubble anymore. It will break apart much faster. So if we were doing drops of water on a penny with a surfactant, we wouldn't be able to hold as much water in that same space. Things that can act as a surfactant are going to be stuff like soaps, detergents, and oils. All of those kind of non-polar substances are going to break apart the hydrogen bonding. Soaps and detergents a lot of times will have like a polar end and a non-polar end. So instead of the water molecules attracting one another, they can be attracted to the soap or detergent particles. And then we're going to switch over vapor pressure. So we said that water has a low vapor pressure. So what vapor pressure is the result of molecules escaping from the surface of a liquid and entering the vapor stage. So this is going to be evaporation. Is dealing with vapor pressure. So it's basically how easily a substance will evaporate and go from being a liquid into being a gas. Low vapor pressure means it's harder to evaporate than something with a high vapor pressure. If something has a high vapor pressure, it's going to evaporate very quickly. So the hydrogen bonds in water hold the molecules together, so it's harder for them to escape the liquid. That's why water's evaporation is relatively slow compared to some other substances. So stuff like rubbing alcohol has a relatively high vapor pressure. So if you had rubbing alcohol and water next to one another, the rubbing alcohol would evaporate faster. I still have a few people writing, but remember and kind of note that both of these kind of unusual properties of water are due to those hydrogen bonding. It's all about the water molecules being attracted to one another through those hydrogen bonding that has a higher surface tension and a lower vapor pressure. All right, so that was kind of looking at properties of water as a liquid. There are also special properties of water whenever it is frozen. So as a solid or ice. One of the most common ones that people know about is solid water, ice, floats in liquid water because it's less dense than the liquid water. So remember, substances that are more dense tend to sink. Substances that are less dense tend to float. This is unusual. Normally, the solid is going to sink in whatever its liquid is because solids tend to be more dense than liquids. What happens with water, why it does the opposite, why it doesn't behave as other things may, is yet again due to those hydrogen bonds. So hydrogen bonds, remember, holding water molecules together. So whenever they're in the solid state, they're arranged kind of like a honeycomb. So here's where that bent shape of water comes in. So we had the water with the hydrogen and the oxygen. That's going to be attracted to another water molecule. And I'm just going to put dots showing that it's attracted. And then there will be another water molecule that it's attracted to. Let's see if I can draw this. Okay. So whenever this occurs, you have all these hydrogen bonds attracting one molecule to another. And whenever they freeze, they link up, kind of making this honeycomb shape. Well, inside this honeycomb shape, once all the molecules are arranged, is a pocket of empty space. Empty space gets filled up with air. So whenever water freezes into ice, the way it arranged allows for air pockets in there. So the air makes the ice less dense than the liquid, which is why it ends up floating versus sinking. No, just know that it links up, leaving empty space due to those hydrogen bonding. It's pretty much, if you know that hydrogen bonding controls all the special properties of water, that's most of it. I know it's a little weird to draw because you have to arrange them a certain way, but I just wanted to show y'all how it's arranged. But I'm not going to expect you to draw it. And I think everybody's with me. If I'm going off and leaving anybody, please let me know. So we kind of talked about the special properties of water. Where we deal with water most of the time is whenever we're dealing with solutions. So anytime we've done a lab throughout the whole semester, we do deal with solutions. So remember, solutions we talked about way back in Unit 1, where those were those homogeneous mixtures that we kind of dissolved one substance in another, and you can't tell where one substance ends and where the water is. It's all kind of uniform throughout. So these are all aqueous solutions that we've been dealing with. So aqueous solution means that you have water that contains dissolved substances. So we dissolve things in water. There are two parts of a solution. We have the solute and the solvent. The solvent, which in aqueous solutions is water, is going to be the substance that is dissolving minerals or compounds. A lot of times we'll say it's the dissolving medium. It's what everything is being dissolved in, is the solvent. Whereas the solute is the substance that's being dissolved. So like if you've ever had a sore throat and they tell you to gargle salt water or something like that, whenever you put the salt in the water, the salt is the solute, the water is the solvent. You stir them together to where you can't tell where one ends and the other begins. So you make that aqueous solution before gargling or something like that. Whenever we're looking at forming a solution, there are some kind of factors that allow solutions to form. So there are three factors that determine how fast a substance will dissolve. A lot of these are kind of common sense things that you already know. You may just not think of them in terms of one solution formation factor is going to be stirring. So whenever you're stirring, it's going to speed up dissolving by bringing new solvent in contact with the solute. So if you've ever tried to make like a pitcher of sweet tea or a pitcher of lemonade or something like that, and you pour the sugar in, if you just dump the sugar in and don't stir it, it's just going to sit there and kind of settle at the bottom. But as soon as you stir it, there's new liquid coming in contact with the sugar, so new solvent and solute connections. So it's going to dissolve much faster once you stir it. Another factor is temperature. Generally, the higher the temperature, the faster the dissolving. So kind of like I said, if you're trying to make sweet tea or something like that, the sugar is going to dissolve better in hot tea versus cold tea. And then the last one that we looked at is particle size. So generally, the smaller the particles, there's going to be a greater surface area, so the substance is going to dissolve faster. So this would be most of the time whenever we buy sugar, it's the granulated sugar, it's the tiny little crystals. Whereas some places you can buy like sugar cubes, but the granulated crystals are going to dissolve much faster than if you had the sugar cubes. Because in a sugar cube, only the outside particles can be dissolved. Those inside particles are going to be untouched. Yeah, for a while. Eventually they will dissolve, but not as quickly as if we were using the granular sugar. Let me scroll down a little bit so my people in the back can see. That slide kind of shifted down a little bit. And when we're forming solutions, we're going to be looking at solubility. So we dealt with solubility a little bit during chemical reactions when we looked at our solubility rules to see what type of things would dissolve and what type of things would not dissolve. But in terms of solubility, it looks at the amount of solute that will dissolve in a given quantity of a solvent at a specified temperature and pressure to produce a saturated solution. Solubility tends to be written in grams per liter or grams per milliliter. And what it means by a saturated solution, whenever something is saturated, it contains the maximum amount of solute for that quantity of a solvent. So it's dissolved as much as it possibly can, and it cannot dissolve anymore at that given temperature and pressure. So overall solubility just looks at how much can a substance dissolve to become fully saturated, where it cannot dissolve anymore at that temperature and pressure. With solubility, we're producing solutions, and sorry, I'm not sure what happened with my slide. There we go. So we said a saturated solution has dissolved as much as it possibly can at that given temperature and pressure. We can also end up with unsaturated solutions. These are solutions that are going to contain less solute than its saturated solution. So it holds less solute than it can dissolve. So this is where if we were to add more solute, it can continue dissolving that solute. So this would be where we can keep adding and it will keep dissolving and we won't have any like solid form at the bottom. There are also mixtures of liquids. We're not really going to deal with this at this point in time. This is one of the things that we kind of decided to leave out or skip. But liquids can dissolve one another as well, depending on their properties. So liquids that are miscible dissolve in one another. Things that are immiscible are liquids that are insoluble in one another. So this would be like water and oil. That's kind of a common one where people know that they don't mix. So if you're walking a parking lot after it rains, you kind of have the big water puddles and then any like oil or gasoline's kind of going to be floating on the top because the two will not dissolve in one another. And that's because they have different intermolecular forces, different properties that won't allow them to dissolve in one another. So we're going to talk about a little bit of solubility factors later, but you don't necessarily need to know the terms miscible and immiscible. We're going to be dealing mostly with the like solid being dissolved in the liquid, not the liquid being dissolved in the liquid. And general factors that affect solubility, the big thing is going to be temperature. So solid and liquid solubility are affected only by temperature. So generally at a higher temperature, you're going to be able to dissolve more of a solid or liquid. And you'll kind of see this in a minute where we look at solubility curves. We can also deal with solubility of gases. Gas solubility is going to be affected by temperature and pressure. So we kind of skipped gas laws this time around. But gases, remember the particles are far apart, spreading and moving very quickly. So one thing that you'll notice is gases tend to be more soluble at lower temperatures, whereas everything else tends to be more soluble at higher temperatures. So I'll kind of show you that when we get to our solubility curve as well. So with temperature, like I said, in general, as temperature increases, solubility increases. So generally, the warmer something is, the more it can dissolve. A few substances will decrease. These tend to be gases. So gases tend to have a lower solubility at higher temperature, simply because the particles are moving too fast to be dissolved. Whenever we're dealing with temperature, we can also create a supersaturated solution. So we said saturated solution dissolved all it possibly could. Unsaturated solution could still dissolve more. It held less than it could possibly dissolve. Supersaturated solutions contain more solute than it should theoretically be able to dissolve at a given temperature. So these are things that whenever they're heated, they're a liquid. But as soon as they start cooling down, they're going to crystallize and form a solid. This is actually one of the processes used in making rock candy or hard candies and stuff like that. They superheat it to make it dissolve all the sugar, and whenever it cools, all the sugar crystals come together to form that rock candy. Okay. And here's our last slide. So solubility curves. This is something that you don't have to draw or anything like that, but you're going to need to be able to read. Let me see if I can zoom out a little bit. I'm going to make my picture a little bit smaller. Whenever I transferred over, it was a little too big. There we go. All right, so solubility curves. Like I said, this is something that you just need to be able to read and get information from this graph. So dealing with the solubility curve, you have the temperature going across the bottom. You have the solubility on the sides. This looks at how many grams of that salt, grams of that compound, can be dissolved in 100 grams of water. So 100 milliliters of water, how much can be dissolved? And then each line, so here it's a different color. On most of our stuff, it will be in black and white. But each line represents a different substance. So things that you might be asked to find on a graph like this. It might ask which is the most soluble at a given temperature. So the most soluble at a given temperature is going to be whatever is the highest at that temperature. So if I asked what's the most soluble at 10 degrees Celsius, we'd say, okay, 10 degrees, the line that's the highest is this sodium nitrate, the NaNO3. You could also be asked which is the least soluble. So that's the opposite. At whatever temperature, which line's the lowest? So I might say at 30 degrees Celsius, which is least soluble. So 30 degrees, the line that's the lowest is this cesium sulfate. Other things that you might be asked is at a given temperature, how much is dissolved to make a saturated solution? So I might want to know how many grams of KCl can dissolve at, sorry, I'm trying to write and talk at the same time, can dissolve at, let's do 70 degrees Celsius. So we'd say, okay, 70, we need to go up to the line for KCl, which is that dark blue one. So here's the line for KCl. How much can dissolve? That's going to be about 47 or 48 grams. There is kind of an acceptable range of an answer, but we know it's somewhere between 40 and 50, but it's closer to the top. So anything between like 45 and 50 would be an acceptable answer there. It could also ask you for the temperature. So it might want to know at what temp can 70 grams of potassium dichromate dissolve. So we'd have to say, okay, 70 grams is right here. Potassium dichromate is this kind of navy colored one. So 70 grams is going to be there, which is just past 90. So I'd probably say like 91 degrees Celsius. Somewhere in there would be an acceptable range. So those are pretty kind of straightforward, just matching up the points on the graph. Other things that you may be asked are, is the solution, it might ask if it is saturated, unsaturated, whoops, hang on. Well, so it might ask if it's saturated, unsaturated, or supersaturated. So here you're wanting to know whatever point they give you, because they'll give you a temperature and a solubility. Is it on the line, above the line, or below the line? So here's kind of whatever the line is. If it's on the line, it's going to be saturated. If it's above the line, it's going to be supersaturated. If it's below the line, it's going to be unsaturated. So kind of show you how this would work. Sorry, I'm trying to pick one that's a relatively easy number to see. All right, let's say that we have let's say that we have 42 grams of KCl at, let's do 45 degrees Celsius. And we want to know, is it saturated, unsaturated, or supersaturated? So we'd say, okay, 45 degrees Celsius is right here in the middle. Go up to 42 grams, which is going to be somewhere here. And we're looking at where is that point in comparison to that line for KCl. It's slightly above the line, so we would say that that is supersaturated, because that point that it gives us is above the line for that substance. We might also have something that wants to know, there's 50 grams of lead 2 nitrate. At 20 degrees Celsius. And it wants to know, is that saturated, unsaturated, or supersaturated? So we'd say, okay, 20 degrees, go up to 50 grams, which is going to be here. So that point right there, and we want to know where is that in relation to the line for the lead 2 nitrate, which is that yellow line. It's below the line, so this would be an unsaturated. It can still dissolve more. If it were to fall directly on the line, it would just be saturated. So those are types of questions that you'll come across in regards to reading solubility curves. There are other things that could be asked about this, but that's a little bit outside the realm of what we're going to deal with this semester. So I did want to show you on your part 1 homework, which you can start tonight. The part 1 homework goes over the solubility curve. So it gives you a solubility curve to reference. So you don't need to look one up or anything like that. You're going to answer questions 1 through 6. So stop where it has the molarity and dilutions practice underlined. So that's not a ton that you have to do based off of solubility curves. But remember, all of these refer to this curve up here. So if need be, make sure, if you print it out, make sure you use a pencil and you can kind of go back and forth. Feel free, you can kind of sit there and put your mouse wherever a point is, or simply put your finger there if you're kind of going over those questions. So it's just the first 6 questions. The next part, the molarity and dilutions, we're going to deal with tomorrow. So tomorrow we are doing calculations, so make sure to have a calculator handy. All of our math stuff this unit has a set formula. So it's kind of plug in and solve for X. So those formulas are on your chemistry reference sheets. So that'll be nice and kind of easy to go through. So you guys have the rest of the period. You can work on this homework. You can probably finish this before the period's over. It's not going to take you a ton of time. Remember that, so first period exam is on the 20th. I know I'm going to have Miss Kincaid's 4th period watching this as well. So the 4th period exam is going to be on the 26th. So they are coming up sooner than you think. So make sure you're getting any makeup work turned in and taken care of. If you owe any quizzes or tests, get those taken care of as well. And other than that, my guys at home, I will let you go and see you tomorrow. I'll stay logged on for a couple minutes in case you have any questions.